Welcome to section 3.1, exponential functions. So in chapter 3, we're going to be talking about exponentials and logarithms. So first off, definition of an exponential function. This is a function like this, f of x is equal to a to the x. In this case, our constant is the base and our variable is the exponent, as opposed to things like x squared, x cubed that we've been dealing with earlier. A is going to be a positive number and a is not equal to 1 because 1 to a power is just kind of useless because it's the same thing all the time. So we just ignore that case. It's called an exponential function with base a and exponent x, and the domain is negative infinity to positive infinity. We can plug in any number we want for x and it's going to be valid. So let's just start by calculating some of these. Let's say our f of x is 1/4 to the x power, and we're asked to evaluate these. Now you can use your calculators as you wish, but just plugging in here, this will be 1/4 squared. And so you square the top and then you square the bottom to get 1/16. Okay. F to the 0. This will be 1/4 to the 0 power. And anything to the 0 power other than 0, 0 to the 0 power is not defined. But anything else to the 0 power is 1. Okay? F of -1. This is 1/4 to the -1 power. When you have a fraction raised to a negative exponent, you take the reciprocal of it and raise it to the positive version. So 1/4 to the -1 becomes 4 to the first power, which is, of course, just 4. Okay. F of 5/2. So this is 1/4 to the 5/2 power. Now, to remind you what a fractional exponent is, the denominator is your root, so this is a square root raised to the 5th power. So this is 1/2 raised to the 5th power, which is 1/32. Okay, now mixing this all together, f of -3/2. This is 1/4 to the -3/2. Let's take the reciprocal of that to make the exponent positive. So I have 4 to the +3/2. So take the square root and then cube it. The square root of 4 cubed is 2 cubed, so that is 8. Okay, now we're going to want to talk about the graphs of exponentials because they tell us a whole lot. And there are two main cases, and it has everything to do with whether your base is larger than 1 or if it is, because a has to be positive, or whether it's between 0 and 1. So what I'm going to do is we're just going to do a special case with 2 to the x. We're going to do a chart here, find our values, and then we're going to plot it so to get an idea of what we're looking at. Okay, let's just start off with our positive exponents because they're easiest. 2 to the 0 power is 1 because that's always true. 2 to the first power is 2. 2 squared is 4. 2 to the third is 8. 2 to the -1 will be 1/2. 2 to the -2 will be 1/4. And 2 to the -3 is 1/8. So let's plot these. If I go to -3, 1/8, that's just barely above my x-axis there. -2, 1/4, it's just slightly higher, and I overestimated that a little bit. Okay. Anyway, even though I got those a little bit off here, basically your graph hugs the x-axis and then shoots up dramatically. Okay. Now it turns out there's no value of x that you could possibly plug in that's going to give you a negative answer. It's just never going to happen because negative exponents create fractions and reciprocals. They don't create negative answers. So it turns out that the x-axis is a horizontal asymptote you're never going to cross. Okay. Now let's look at the case where we have a fraction, something between 0 and 1 as your base. So I do 1/2 to the x power. Well, 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. Squared is 1/4. Cubed is 1/8. And you can see that we're basically going in the opposite direction as to what we have up here. Okay, so 1/2 to the -1 is 2. This would be 4, and this is 8. So let's plot these values. If I have -3, 8, -2, 4, -1, 2, and then 1, and 1/2, and 1/4, and then 1/8, and so on. This graph decreases rapidly, and then it starts to level off again a bit and goes like this. And again, it doesn't matter what your base is. There's no value of x that you can plug in that will give you a negative value. So this also has a horizontal asymptote right there at the x-axis. Okay. This is an example of exponential growth. This is an example of exponential decay. So let's talk about just a summary of our properties here. So in the beginning here, we're talking about just a general exponential. The domain of the exponential is -infinity to +infinity. The range, there's no way you can get a negative answer. So your range is 0 to infinity. 0 is not included. And the entire graph lies above the x-axis. Okay. Now look here. This comes from definitions of exponents, our exponent rules. F of x plus 1. That would mean that you plug in x plus 1 up here instead of x. And by definition, this is the same thing as this because that's x to the first power right there. And by exponent rules, if you're multiplying, you'd add those back together. So this is the same as this, which is the same as a times f of x because that's f of x. So what this means is that the y value changes by a factor of a for every unit increase in x. So really, we're just multiplying by a every time we increase. Okay, so when a is greater than 0, remember when a is greater than 0, that's exponential growth. The growth factor is a because the y values increase by a factor of a for each unit. Okay, so f is an increasing function, so the graph rises to the right. Okay, which we've got here. As x goes to infinity, y goes to infinity. The further out we go on x, the further up we go on y. And as x goes to -infinity, y goes to 0. The further out we go this way, the closer our y values get to 0. And it's opposite when our a value is between 0 and 1, because our graph is going down every time. It's a decay factor of a, and everything here is the opposite. F is a decreasing function, so the graph falls to the right. Okay. As x goes to +infinity, my y value goes to 0. As my x value goes to -infinity, my y value goes to +infinity. Okay. Exponential function is 1 to 1. It does pass a horizontal line test. Okay. So if a to the m is equal to a to the n, then you can set the exponents equal to each other. And that will always work. So if you have the same base and they are equal, then your exponents must be equal. F definitely has an inverse because it is 1 to 1. Okay. The graph of f has no x-intercepts, so it never crosses the x-axis. So no value of x will cause it to equal 0. The graph of f is a smooth and continuous curve. It doesn't jump around, and it doesn't come to any sharp points. It will always pass through the point -1, 1 over a, -1, 1 over 2, -1, 1 over 1/2 is 2. It'll always go through 0, 1, because anything to the 0 power is 1, and the point 1a, because anything to the first power is itself. The x-axis is a horizontal asymptote, okay? And the graph of a to the negative x is the reflection about the y-axis of the graph of y equal a to the x. This comes from our earlier transformations chapter in chapter 1. In fact, we're going to be able to use transformations to graph all of these.